Hello, everyone. Welcome to Physics Lab. This is lab number 4, which is going to be on Newton's second law and frictional forces. And for most of this lab, it's very similar for all my different labs for Physics 206, 207, and 212. There's one additional part at the end when we look at friction where Physics 212 has to do that, but the other two classes don't have to do that particular part, okay? So it's very similar, so I'm gonna use one video lecture for all three classes. So the first thing I wanna talk about is Newton's second law. So let me describe what Newton's second law is, and I'll go to the iPad to do that. Okay, so Newton's second law. Let's say we have an object. Let's say it has a particular mass. I'll just call it m. And let's assume that there's two forces acting on this object. So let's say I have a force F1 acting to the right. So I'll call this F1. And then a force, I don't know, maybe like this, F2 acting in that direction. So I have two forces acting on the object. Now, what I want to find first is the net force, the sum of those two forces acting in on that particular mass. So remember how to do that, right? We add forces because they're vectors, so we add them vectorially. So we add them tip to tail. So if I move the tail of F2 to the tip of F1, it'll look something like this. And then if I draw a vector from the tail of F1 to the tip of F2, that's going to be my net force. So this is F net. Okay, or some people also call that the sum of the forces. Now, what Newton's second law says is that net force which again is also equal to the sum of all my forces. I added up all those vectors. That's equal to the mass times the acceleration of the object. And notice that the net force is a vector and the acceleration is a vector. So they're going to point in exactly the same direction. So in this case, this mass is going to accelerate in this direction, right? The same as the net force. Okay, so that net force will cause that mass to accelerate in the same direction that the net force is in. Now, another thing, since this is a vector equation, right, we can attach a coordinate system. And in fact, we do want to do this typically when we analyze these types of problems. You attach a coordinate system, and then we can resolve the vectors into its components, into its x component, its y component, and if we had 3 dimensions, also the z component. So this one vector equation over here, so this equation is really 3 equations in one, right? I could write this as the sum of the forces in the x equals mass times the acceleration in just the x direction. And then we have the sum of the forces in the y equals the mass times the acceleration in the y direction. And then the sum of the forces in the z is equal to the mass times the acceleration in the z direction. And for most of the examples in lab and in lecture, they're going to be just 2-dimensional examples. So really, we only need to worry about the x and y directions. We won't typically deal with 3 dimensions. Okay, so that's Newton's second law. It's F equals ma, but remember F is the net force, right? The sum of the forces equals ma. Okay, so in this lab, we have a system where we have a cart. The cart is on an air track, right? So this is the air track right here. Attached to the cart is a string, and that string goes over a pulley, and then we have a suspended mass. So this is a mass, like basically it's a hanger with some masses on it. And the cart starts at rest, right? Which means the suspended mass also starts at rest. You turn on the air track, and then we release the cart So we let it go, and it's going to accelerate to the right, and the suspended mass will accelerate downward, right, with the same rate. So this will accelerate to the right, suspended mass will accelerate downward. So the idea for the first part of the experiment is we want to calculate that acceleration experimentally. So I'd highly advise you guys to watch my little video here on how I collected the data, how I collected the experimental data, how I got those accelerations. And then the second way that we're going to get the acceleration is we're going to calculate it theoretically. Like theoretically, if we have the system of these two objects, what should the acceleration be? And I'll do that in a minute or so. Okay, so we'll calculate the acceleration theoretically. We also collect it experimentally using what's called a smart timer. Again, you want to watch that additional video. And then the goal is going to be to compare what we got experimentally for the acceleration to what we get theoretically. Okay, so let me start and show you how to derive the theoretical acceleration of that system. Okay, so let's say this is the air track, and I have the cart, which is on the air track. It has a particular mass. I'll just call it M1. And then we have a pulley here. And then connected to the cart is a string, and it goes over the pulley. And then it's connected to a suspended mass. And that suspended mass I'll call M2. Okay, and when you release the cart, what's going to happen? Well, this is going to accelerate to the right, some acceleration, and the suspended mass will accelerate with the same rate down, right? Same rate because it's connected by the same string. So the goal is to figure out that acceleration. Okay, we want to calculate that acceleration theoretically. So the way that you do this is you isolate each object in the system. So I'm going to start with the cart. So I'm going to draw the cart. Right? It's isolated. And now I want to figure out all the forces acting on that cart. So what are the forces acting on the cart? Well, we definitely have gravity, right? The gravitational force, which is the weight of the cart, and that acts down. So this acts down, so I'll say W. And we know that's really equal to mg. And then we have a force that the air track exerts on the cart perpendicular to the air track, right? Perpendicular to the surface. And that's called a normal force. That's going to act up. Remember, normal means perpendicular, so it's perpendicular to the surface. And then finally, we also have a string that connects to that cart, right? So it's exerting a force on the cart. So we call that a tension, right? There's a tension in the string, and that's acting to the right. So we have a tension acting to the right. And normally, you'd also have to include a frictional force, right? You would include what's called a static frictional force. But why do we not have a frictional force? So normally there would be a frictional force in this direction, right? Going to the left, opposing the motion. And it would be called a kinetic frictional force, which we'll talk about at the end of this lab. Why do we not include that? Because we're using the air track, right? So we're assuming that friction is negligible in this case. Okay, so now what I want to do is I want to attach a coordinate system, some convenient coordinate system to analyze this cart. Well, I know that it's going to accelerate to the right. So I think what I'll do is I will make my x direction, my positive x direction, go towards the right. So it'll be like this. And that means the y will be perpendicular. So this would be the y direction. So there's my coordinate system. And now I want to apply Newton's second law to both the x direction and the y direction. All right. So what I'll do, actually, I'll do the y direction first. So from Newton's second law, we know that the sum of the forces in the y direction has to equal the mass of that cart, which was m1, times the acceleration in the y direction. So for the sum of the forces in the y direction, what that means is I want the y component of all those forces, right? So I want the y components of all those vectors. So I could write this, in general, I could write it as I want the y component of the normal force plus the y component of the tension plus the y component of the weight, and that's got to equal m1 ay. Well, what is the y component of the normal force? Well, if you look at this diagram, right, the normal force is acting completely in a positive x direction, right? If you find those components, it has no component in the x, it's all in the y, right? The entire normal force is in the y. So we could say that the y component of normal force is all of n. What about the tension? Well, since it's acting right along the positive x-axis, right? If we project this onto the y-axis, we have nothing, right? There's none of that vector lies in the y direction. All of it lies in the positive x. So if I want the y component of tension, that's going to be 0, right? None of it lies in the y direction. And then finally, for the y component of the weight, since the weight vector acts downward, right, and there's no component in the x, it's all going to be in a y, and it's going to be negative, right, because it's acting downward. So I'll write this as negative mg, and that's got to equal m1 ay. But this cart is not accelerating in the y direction, right? It's not leaving the air track in the y direction. So its acceleration in the y direction is going to be 0, okay? And then if I solve this, I can move the mg to the other side, and I'm going to get that the normal force, in this case, is just equal to the weight. Okay, and that actually would be very important if we had friction, because friction depends on that normal force. For this particular case, it doesn't really matter. It's a true statement, but it's not going to really help us. So now I'm going to go to the x direction. So I have sum of the forces now in the x direction equals m1 ax. So again, I'll look at all the components. I want the x component of the normal force, the x component of the tension, plus the x component of the weight. That's got to equal m1 ax. Okay, well, what's the x component of the normal force? How much of that normal force vector was in the x direction? None of it, right? It's all in the positive y. So this is going to be 0. How much of the tension is in the x direction? Well, the entire vector is in the positive x direction. So this will be plus the entire magnitude. I'll call it t. And how much of the weight is in the x direction? Well, it's all in the negative y direction. So none of it is in the x. So this is also going to be 0. And that's got to equal m1. And then in this case, the ax, I'm calling a, right? So remember at the beginning, I'm really finding a. That's the same as ax. So I'll just write this as a here. So the first equation, and this is an important equation, is saying that t is equal to m1a. I'll box that. Okay, so that was the analysis on the cart. Now let's look at the suspended mass. So here was a suspended mass. Remember, it had a mass of m2. And in this case, what are the forces acting on it? Well, there were only 2 forces acting, right? You had the gravitational force, which is its weight, acting down. So I'll call this W2 is equal to M2G. I guess up here I really should have wrote, this is W1, right, is M1G. So W2 is equal to M2G. And then the only other force acting is the tension, which is acting up. And these again are vectors, right? So tension is pulling up, right? Because the string is attached to that suspended mass. And that's it. Those are the only 2 forces acting on that suspended mass. So because I know it's accelerating in this direction, right, A is in that direction, maybe a convenient coordinate system to use here would just be to call the downward direction positive x. So, and we're free to do that, right? So I could just call this direction positive x, which means this direction would be the y direction. Okay, so now I'm going to apply Newton's second law again. I have the sum of the forces in the y. That's got to equal m2 now, right? AY. Well, I want the y component of the tension plus the y component of the weight. That's going to equal m2 AY. Well, remember, I'm calling y, right? I define my coordinate system so y is perpendicular. Are there any forces acting in the y direction? No, these are both either in a positive x or negative x direction, right? These two forces, there's no component in the y. So this equation simply says that 0 plus 0 equals m2ay. We know it's not accelerating horizontally, right, in the y direction. So this equation just says 0 equals 0, which is true, but it's not going to be very helpful. So now let me turn towards the x direction. So I have sum of the forces in the x direction equals m2ax. So now I want the x component of the tension plus the x component of the weight. That's got to equal m2ax. So what is the x component of the tension? Well, the tension is acting, based on my coordinate system, it's acting in a negative x direction, right? And the entire amount is in a negative x direction. So this is going to be negative t. And then what is the x component of that weight of W2? Well, all of it is acting in the positive x direction, right? So that's going to be m2g. And that's got to equal m2. And then what's the acceleration in the x direction? That's what we're calling a. So this is the second, right, really important equation. Now, one thing to be aware of here is that the tensions, so the tension in this first equation and the second equation, because, let me go back to the picture here. Because we're assuming that this is like a lightweight pulley, it has a very low moment of inertia, it's a lightweight string, we can assume that the tensions are equal. So the tension is equal throughout that entire string. Okay, so those T's are really equal in this case. All right, so we're getting there. So remember, the whole goal here is to solve for A, the acceleration of that system. So let me write down my two equations now. I have T equals m1a. And then I have minus T, right, plus m2g is equal to m2a, right? So basically, I have two equations by two unknowns, right? We know the masses. I can mass these. I can mass the cart and I can mass the suspended mass on the scale, which I did. So we have those values. I know what G is, right? If we're using CGS units, G is going to be 980 centimeters per second squared. But I don't know tension. I don't know acceleration. But I have two linear equations in terms of tension and acceleration. So how do I solve these? Like I want to solve for A ultimately. Well, one thing you could do is you could use substitution, right? Remember, there's many techniques like substitution, elimination. You could use matrices. So there's many techniques for solving two equations by two unknowns. But the easiest might be just substitution. So since in this first equation, I know that T, tension, is equal to M1A, I can take that expression, M1A, and where I have a T in the second equation, I can plug in M1A, right? So then this becomes, so I'm plugging this in for T here. So this becomes minus M1A plus M2G is equal to M2A. Now let me bring my, I want to solve for A, so I need to get the A's together, so I'll add M1A to both sides. So I have M2G is equal to, I'll write this as M1A plus M2A. And now the A is common, right, to both terms on the right-hand side, so I can factor it out. So I have A times M1 plus M2. And then finally, I can divide, if I want A by itself, I can divide both sides by that sum, M1 plus M2. So this will cancel. And then what I get, I'll write A on the left-hand side, is equal to M2G divided by m1 plus m2. And that was what we're looking for, right? This is the theoretical acceleration of that system. So when you're asked to calculate the theoretical acceleration, that's what you want to use to calculate it. Okay, so if you look at this first table, these are simply the masses that I recorded by massing the cart and the suspended mass on a scale. And in this first part of the experiment, there were two conditions. The first condition was the mass of the cart by itself. And then we made it a little heavier, a little more massive by adding these two weights to it, these two cylindrical weights to it. So it's a little heavier. So the mass of the cart by itself was 189.3 grams. And then with the two weights, it was 289.7 grams. And then for the hanger, we kept that constant, right, for both conditions. It was just a hanger plus a small metal weight and ended up being 6.9 grams, right? So you have all that data. Then again, make sure you watch my video to see how I got this information here, these accelerations. So I got them experimentally by using what's called a smart timer. I did 10 trials for each of those conditions. Condition 1 was the mass of the cart by itself. Condition 2 was the mass of the cart with the two weights. Okay, so first question. I want you to calculate the acceleration, the average acceleration for both conditions. So just average these 10 values. Make sure you round to 1 decimal place, right? So these should all be rounded to 1 decimal place. Then I want you to compute the percent experimental accuracy. So I gave you these other rows here so you can find, remember you have to find all the absolute deviations first, like how far each one is from the average. Then you average these absolute deviations, round to 1 decimal place again. And then finally, remember it's the average absolute deviation divided by your average acceleration times 100. That will be your percent accuracy. Okay, then I want you to calculate the theoretical acceleration, right, from that formula that we just derived. I'm also calling it predicted. So theoretical is like predicted acceleration. So you're simply going to use that formula that we derived. It's also in the handout here. It's m2g over m1 plus m2. So you're going to plug in your masses. Remember, m2 is the hanging mass. So that's 6.9. m1 is going to be the mass of the cart, which is either 189.3 or 289.7, depending on what condition you're calculating for. Okay, once you have those, right? So basically these two values right here from this table that you averaged, these are going to be your experimental accelerations for your two conditions. So you can just copy this value and that value into this table. The predicted acceleration are your theoretical accelerations that we got from that formula. So you're going to write those in here. And then finally, question 3 is you want to compare these two values by computing a percent experimental error. And remember, when you compute a percent experimental error, you find the difference between these two values and you take the absolute value of it, and then you divide by the predicted and then times 100, right? So you're going to compare them by computing two percent experimental errors, and make sure you show me those calculations. Okay, and make sure you show me the calculations for these predicted or theoretical accelerations as well. All right, then there's a question just in general. So it says, if you maintain the suspended mass, which is what we did in this case, right? We kept it the same for both conditions, but increase the mass of the cart by adding those two weights. What happens to the acceleration of the system compared to when the cart had no weights? So you can either look at your results to answer that question, or you could look at the theoretical equation here, right? If M2 stays the same and you increase M1, what's going to happen to A? All right, so you want to make sure you answer that question. And the hint is it's either going to stay the same, increase, or decrease. Okay, for the second part of the experiment, in this case, what we did was we kept the mass of the cart the same for all 4 conditions. So in fact, it was the mass of the cart plus the 2 cylindrical weights. We left the 2 cylindrical weights on. And what we varied for the 4 conditions now was the mass of the hanger. Okay, so condition 1 was the hanger plus a small metal weight. Then condition 2 is the hanger plus a small metal weight and a large plastic mass. So basically, we're increasing the mass a little bit over these 4 conditions. Okay, so I measured those masses for you, so you have them all on this table here. I again performed, in this case, 5 trials where I experimentally got the acceleration, right, for each of those conditions. So what I want you to do for this question, question 6, is compute the average acceleration, just like you did before. Make sure you round to 1 decimal place. Right, so find the average acceleration. Then you want to compute the tension in the string, right? And this actually comes from that second equation that we derived when I was using the iPad when I showed you that derivation earlier. But it's just this formula. It's the tension in the string is going to be the hanging mass, so whatever this value is, right, depending on your condition, times G minus A. Well, G is, of course, is 980. That's going to be a constant, so 980. And then the A is your average acceleration here. So you're going to do 980 minus your average acceleration times this mass, times m2, and that will be your tension. Now notice that because we're in CGS units, centimeters, grams, seconds, and not SI units, tension, instead of being in newtons, it's in dynes. And just because of how the numbers work out, these are going to be very large numbers. You're going to find that this is around, 6,000-ish. And it'll increase all the way up to, like, I think it's 17,000. So don't worry if you actually get large numbers. You should get large numbers. It's because the units are in dynes. Okay, once you have these 2 columns calculated, and I would show me, some calculations here. So once you have those calculations, you're going to plot tension versus acceleration. So on Pascal Capstone, plot tension versus acceleration. So that means acceleration will be on the x and tension will be on the y-axis. And make sure you include 0, 0, okay, as a data point as well. So you have 0, 0, and then these data. So x, y. Theoretically, right, because of this equation, we know the first equation we derived was tension equals the mass of the cart times acceleration. This should be linear. If I plot tension versus acceleration, it should be linear, right? Because this is a linear equation. So once you plot it, you want to do a linear fit. And what does that slope represent? Well, that slope should represent the mass of the cart. And in fact, in this part of the experiment, remember, it was the mass of the cart with the 2 cylindrical weights. So now we want to compare, because we actually had that value twice, right? The mass of the cart with the 2 weights, we can get directly by massing it on a scale, which I did earlier, and I just copied that value down here, so it's 289.7. Think of that as like the experimental or measured mass of the cart. And then the predicted mass of the cart with the 2 cylindrical weights is this value from the slope of the graph. So when you plot your graph and you figure out that slope, that's going to be the predicted mass of the cart with the 2 weights. And then I want you to compare these two by computing the usual percent experimental error, okay? And then for this one, I would say divide by the predicted, right? We always divide by the predicted. So we're going to assume that this is a predicted mass of the cart with the 2 weights. And hopefully you get a fairly small error here. Okay, so the next part is I wanted to do a little bit with having you collect some data. So again, the only way that we can realistically do that this semester is using a simulation. So you're going to go to the simulation, right? It's another one of those PHET simulations from Colorado, which are very good. This one's on forces in motion. And you want to follow these directions here, and that will allow you to answer question 7, okay? Let me show you what to do. So I'll go to that simulation and show you how to set it up. Okay, so we go to the simulation. You want to choose, in this case, you want to choose acceleration. And then what we're going to do is check off, we want forces, we want to see some of the forces, values, masses, and speed. The only thing we don't want to see is acceleration, right? Later on, we want that, but not right now. And then to make this crate a little bit more massive, we're going to put the child on the crate. All right, then what we're going to do is set the applied force. So this is the applied force here, so that it's 300 newtons. So you can either go up by ones or go up faster. This goes up by 50s, the double arrows. So you want to go to 300 newtons. So now you can see that the crate and the child are accelerating to the right. So there's an applied force, right, that the person's exerting to the right. There's a kinetic frictional force to the left. So that will give you a net force, right? And you know that the net force has to equal mass times acceleration. So you want to use Newton's second law to figure out what the acceleration is. All right, then, let me stop this. Then what you'll do is you'll do the same thing, right? So put the child on, so it's a little more massive here. Again, go to 300, and now click acceleration to get the acceleration value from the simulation. Then you want to compare, so that would be that value right there. Then you want to compare what you calculated to that particular acceleration. And it should be exactly the same or very, very, very close. Okay, for the second part, let me click off acceleration. So after the person lets go, so they're accelerating. At some point, they're going to let go. And now the crate is decelerating, right? So the only force acting on it is the kinetic frictional force to the left, right? So now you want to calculate the acceleration in this case, and then go back and do the simulation again after the person lets go, but click on acceleration to get the value that the simulation is giving you and compare those two values. Okay, so basically you're using Newton's second law to calculate the acceleration, and then you're measuring it directly by clicking on acceleration here so that you can compare those two values. All right, so you're going to do that with the crate and a child, and then later you're going to do the same thing, but you're going to put two crates, right? One crate on top of one another, and it's the same thing. When the person is pushing the crate and accelerating it, calculate the acceleration, and then measure it by clicking on this value here. And then after the person's done pushing, the two crates are going to decelerate. They're going to slow down. So then you want to calculate that acceleration and then measure it by clicking on this value here. All right. Hopefully that made sense. Okay, so again, here's question 7. Here's the table of data. You're going to calculate the acceleration when the person is exerting a force on it. Then after they let go, and the only thing acting on it is the kinetic frictional force, and you're going to measure it by clicking on the acceleration button. Then you're going to do the same thing when you have the two crates, right? So this is the crate and the child, and this is the two crates. And hopefully you get very similar, if not exact, values when you do that. Okay, the next part of the lab is on frictional forces. So let me go back over to the iPad and describe friction and frictional forces. Okay, so first situation, let's say we have an object, it's on a flat surface. So we're gonna have like a wooden cart, right? That's gonna be on that wooden track, which is gonna be kept horizontal, so it's a flat surface. And let's say I exert a force to the left, so I pull on it with some force F. Let's assume that the cart is not moving, so not moving. Well, because it's not moving, right, the acceleration would have to be 0, which means the net force would have to be 0. So there must be some force that's resisting the motion that's pointing toward the right, And actually, it has to have exactly the same magnitude as F, but going towards the right. So I'll draw it the same length. And this is what's called a static frictional force. So we call it F sub S. So it's a static frictional force. And then if I pull harder, so again, let's assume it's still not moving. So this object, the box or the cart is not moving. Let's say I pull harder now. Then it turns out that static frictional force is going to increase to balance out the force I'm pulling with. Because again, the net force would have to be 0, right? If I add those two up, I have to get 0 because it's not moving, it's not accelerating. And you can keep doing this until the object is on the verge of motion. So I'll say on verge of motion. So let's say I pull really hard now to the right with the force F. Then again, there's a static frictional force that's resisting it because it's still not moving, although it's right on the verge of motion. If I pulled any harder, it would start moving, but it's still not moving yet. So I still have a static frictional force. But because it's the largest that the static frictional force can be, we call this Fs max. So Fs max, it's like the maximum static frictional force. Okay, and notice that the static frictional force can increase from 0, like if you're not pulling at all, there's no static frictional force, all the way up to Fs max. So that's why you'll see the static frictional force defined to be Fs is greater than or equal to 0, less than or equal to Fs max. Right, so it can vary. In this case, it was very small, right? If there's no force at all, this would be 0, right? There'd be no force resisting it, and it can go all the way up to a maximum value. And then the other situation is if I'm pulling on the cart, let's say it's moving now, but I'm going to do a special case. Let's say it's moving at a constant velocity. So if I pull it with some force F and it's moving with a constant velocity, well, again, if it's constant velocity, that means there's no acceleration. So the net force has to be 0. So what's the force that's resisting in this case? It's a type of frictional force. And since it's moving, we call this a kinetic frictional force. So this is called F sub K for kinetic. So kinetic is when it's moving, static is when it's not moving. And in this particular example, the magnitude of F, if I calculate what that magnitude is in newtons, that's going to be the magnitude of my kinetic frictional force. Why? Because it's moving at constant velocity. It's not accelerating. So the net force, if I add those two together, it has to equal 0. Okay, now there are some models for frictional forces, and it turns out that you can model Fs max and Fk as being proportional to the normal force. And what the proportionality constant, we usually use mu. So for the static frictional force, we use mu s, and it's times the normal force. So it's proportional to the normal force. So this mu s here is the coefficient. Let me make some room here. This is the coefficient of static friction. And the n here is the normal force. Normal force. Okay, now that these coefficients, these are just numbers, right? They represent something about the two surfaces that are sliding over one another. In this lab, it was a wooden cart that had these leather straps on the bottom, and it was sliding on a wooden ramp. So really, we were looking at the friction between the leather straps and the wooden ramp, right? So there was some coefficient that defined the maximal static frictional force. And then for the kinetic frictional force, there's a similar relation, except it has its own coefficient called mu k times the normal force. And this mu here is called the coefficient of kinetic friction. Okay, so actually what I want to do now is I want to remind you what normal force is, right? So in this example, it's actually really straightforward. If I have the cart on a flat air track, or sorry, not a flat air track, a flat wooden track, right? Because it's sliding on a wooden track. So a cart on a flat wooden track. Well, there's only two forces acting in the vertical direction, right? I have the weight acting down, it's a vector, it's equal to mg. And I have, in this case, the normal force is the force that the surface exerts on the object perpendicular to the surface. So the normal force is acting up in this case. And then if you applied Newton's second law to the y direction, and there could be other forces acting on the x direction, I won't draw them right now. Let's assume it's just sitting there. So if I look at the sum of the forces in the y, that's got to equal MAY. So in this case, I want the y component of the normal force plus the y component of the weight. That's got to equal MAY. But the y component of the normal force is, since it's all in the y direction, right? If I call this my coordinate system, this is say y, and this is x, then all that normal force is in the positive y direction. So this is just positive n. And then the y component of the weight is actually minus mg, right? Because it's acting in negative y direction. And that's equal to 0 because it's not accelerating in the y direction. That wooden cart is not leaving the wooden ramp at all. And then, of course, we can solve for n now. And it turns out n in this case is simply equal to the weight, right? The weight of that wooden cart. Now, this isn't always necessarily the case, right? When the ramp is on an incline, the normal force is definitely not equal to the weight. It's only equal to a portion of the weight, right? So it's more complicated. But in this case, when it's on a flat surface, there's no other forces acting in the vertical direction in the y direction, then the normal force is equal to the weight. So that's going to be true for this part of the lab. The normal force will just be equal to the weight. All right, now which force is larger, right? So if you look at the maximal static frictional force or kinetic frictional force, which one is larger? Well, let me give you sort of an everyday example. Let's say you're trying to move a large piece of furniture, right? Is it harder to initiate the motion, like right when it's on the verge of moving, or is it harder to move it while it's sliding already? Is it harder to get it started or to push it while it's already sliding? And it turns out, probably from experience, you guys have experienced this, right? That it's harder to initiate the motion, right? So it turns out that Fs max should be greater than Fk. So the maximal static frictional force should be greater than the kinetic frictional force. And that in turn implies that the coefficient of static friction must be greater than the coefficient of kinetic friction, okay? And really in lab today, in this lab, we're going to measure the coefficient of static friction and the coefficient of kinetic friction. That's sort of the goal for this particular lab. Okay, let me go back to the handout. Okay, so make sure you watch my video, my quick little short video on how the data was collected for this particular section. Basically what we did was we used a force sensor, right? And we pulled on the cart, and initially, right, you're pulling harder on the force sensor, but the cart's not quite moving. And at some point it gives, So the highest force is going to be the maximal static frictional force. And then we keep pulling the cart, but now at a constant velocity. And then that force that we're recording from the sensor is going to be equal to the kinetic frictional force. Okay. Actually, let me go back to the iPad for a second to show you what this graph looks like. And you can also look at that video. If you look at the second video here, here's where I analyze Fs max and Fk from the graph of force versus time. But let me just show you this quick on the iPad. Okay, so if we plot force in newtons versus time in seconds, when I'm pulling on the cart, right, with that force sensor connected to it, at first the cart is not moving, but the force is going to be increasing, something like this. It'll reach a peak, it'll drop, and then now if I pull with constant velocity, it kind of plateaus, maybe something like that. And then when I stop pulling, the force goes back down to 0. So basically, here's where, let me dividing line here. This is where the cart is not moving. So the force is increasing, but the cart's not moving. And here, after that red line, is where the cart is moving at a constant velocity. I'm pulling it at a constant velocity, that wooden cart. Okay, so how do I get those measures of Fs max, the maximal static frictional force, and the kinetic frictional force? Well, the peak of this graph right here, that peak, that is Fs max. So when I did that graph, I found the peak of the graph. And then sort of the average of this plateau, somewhere in here, right, the average of that, that's when I'm pulling at a constant velocity, that's Fk. Because remember, the force I'm pulling with has got to be equal to the force of friction that's resisting the motion, the kinetic frictional force, because there's no acceleration. I'm pulling at constant velocity. So that's Fk. So that's how I got those two values, Fs max and Fk. Okay, so here's the table. There were 4 conditions, right? It was the wooden cart, and I put 2 square weights on it to make it a little heavier. Then the second condition is a little heavier with 3 square weights, then 4 square weights, and 5 square weights. So it's a cart with 2 weights, 3 weights, 4 weights, 5 weights. These are the masses, right? So I just massed the cart with those different weights on them on the scale. So this is the mass in kilograms. We're going to use SI units for this lab. So first thing you have to do is you have to compute the normal force, right? So this is question 8. Well, remember the normal force in this case, because the cart is on a horizontal wooden track, the normal force is simply equal to the weight. So to calculate the normal force, it's just going to be mg, right? It's equal to the weight, where g is 9.8. So you can calculate that normal force. Then the maximal static frictional force and the kinetic force, this is what I got from those graphs when I used the GLX sensor, the force sensor. Okay, so that's what I described earlier. This is the peak of the curve, and this is the average of that plateau region. All right, so question 9, and you want to show me your calculations for normal force. Question 9, calculate the coefficient of static friction and the coefficient of kinetic friction, right, for each of these conditions. Well, how do I find the coefficient of friction? I can just rearrange those formulas, right? Remember, the maximal static frictional force was the coefficient of static friction times the normal force. So if I divide both sides by n, that means the static frictional force is simply the maximal static frictional force, which is this value, divided by the normal force. And then the kinetic frictional force is going to be, the coefficient of kinetic friction is going to be the kinetic frictional force divided by the normal force. Right? So that's how you're getting these values, just using these 2 formulas. Now, in theory, remember, these coefficients are pure numbers, right? They should be constants. Now, it's really hard, this experiment, even when I'm doing it very, very carefully. So these won't be exact, but hopefully these will be fairly similar. So these values and these values will be fairly similar. And then you're just going to average them, and that will be your representative coefficient of static friction, and this average will be your representative coefficient of kinetic friction. Okay, now another way, and make sure you show me these calculations, all right? Show these calculations in your group lab reports. Another way that we can get the coefficient of static friction and kinetic friction is we can plot, right? So we can plot Fs max versus normal force, which means normal force is going to be X and Fs max will be Y. Make sure you also include 0, 0. In theory, from the equation, we know Fs max should equal mu s times n. It should be linear, right? So it should be a linear equation. And that slope should be our coefficient of static friction. It should be our mu s. So you're going to do that graph, do a linear fit, and record mu s in this table below, right? This is from the graph. And then also compare to what you got here for an average. It should be very similar, right? There is two different ways of getting that coefficient of static friction. Then you're going to do the same thing with the kinetic frictional force, right? You're going to plot Fk versus n. So again, normal force is X, Fk is Y, include 0, 0, do a linear fit, and that slope should be the coefficient of kinetic friction. That should be your mu k, which you're going to record here. Okay, question 12, compare these. You can compare these, and then it should be the same situation here. Compare these, right? They should be close to what these values are. Which one's larger? Well, we know which one should be, right? Make sure that's true. And then compare the frictional forces. Which one's larger? Well, you could use that example I gave. Like if you're moving a piece of furniture, is it harder to initiate motion or to keep it moving once you've started? So that tells you like which one should be larger, right? So hopefully you will find that when you look at these values. And then question 13 is just give me a couple of examples of some advantages and disadvantages of frictional forces in the surrounding environment. Certainly there's probably easy disadvantages to give, right? Where friction can, if you don't use oil in your car engine, you can seize your car engine, or it creates, fires and stuff. Although that could be an advantage too, right? One advantage would be movement, right? Like if the floor were completely frictionless, could you walk? No, because actually in order to accelerate your body, you're exerting a force back on the floor, and assuming your shoe doesn't slide, the floor is exerting a frictional force. In fact, it would be a static frictional force on you, which is accelerating you forward. So that's allowing you to move. Or even a car driving, right? The road is exerting a static frictional force on the tires to allow it to move. But come up with your own advantages and disadvantages. And then question 14 is just give me a couple of ways that you can use to reduce frictional forces, right? Describe ways to reduce frictional forces. Okay, then there is a simulation part of this experiment. So let me go to the simulation and show you what you need to do for this part. Okay, so for this part, for the simulation with the friction, we're going to choose friction. We're going to go to the same simulation, choose friction. And then you want to click on all of these. So forces, sum of forces, values, masses, speed. And then what you're going to do is you're just going to leave the crate by itself, right? So it's a 50 kilogram crate. That's its mass. You could calculate the normal force, right? Because you know the normal force in this case is simply equal to the weight. So if you can find the weight of the crate, then you know the normal force. You're gonna increase the applied force that the person exerts to the right. I would start at 100. So if you use the gross adjustment here, go to 100, and then start slowly increasing. See how my applied force is like 106. The frictional force is also 106. Sum of force is 0. Right now, what type of frictional force is this? Well, this is a static frictional force, right? And it's increasing to match my force. But at some point, and you have to keep increasing this, you'll find it, at some point, the cart will start moving. So you just increase it by 1. And then when a cart starts moving, then you know that 1 less than that must have been the maximal static frictional force, right? So you keep increasing. At some point, it'll start moving, so it's moving now. If I did that slowly, and I don't want to give you the answer, so I'm doing it quickly, but if I did that slowly, one less than when it starts moving must be the maximal static frictional force. So that will allow you to calculate μs. If you know the maximal static frictional force, and you know the normal force, you can calculate μs. And now once it's moving, right, see how the applied force is increasing, which the net force is increasing, but the frictional force is staying constant. Why? Because this is just now the kinetic frictional force. Once it starts moving, it doesn't even have to be moving at a constant velocity. We did that to find it, but if it's moving, then it's going to have a constant kinetic frictional force. In this case, you can read off that value. We know that the normal force, we can calculate the normal force. So this will allow you to calculate mu k, right? If we know the kinetic frictional force, we know the normal force, you can calculate mu k. All right, so that's it. It's a very simple part of the experiment with the simulation. You're just ultimately going to calculate mu s and mu k based on those two conditions. Okay, so question 15 is calculate mu s, mu k, and fill in this table, right, based on that simulation data. Okay, so now if you're in physics 206, right, sports physics lab, or physics 207, physics movement science lab, that's it. That's all you need to do for this particular lab. If you're in physics 212, then you want to continue watching. There's one other part where we're going to look at the frictional force when the cart is on an incline. Okay. Okay, so in this part of the lab, we have the cart, which is now on the incline wooden track here. And the wooden track is going to be set at several different angles. Actually, 20 degrees, 30 degrees, 40 degrees, 50 degrees, 60 degrees, 65, 70, 75, 80, all the way up to 85 degrees. We're going to keep raising it. And the cart has just a single square mass on it, right? So it has one particular mass, and that's going to stay the same for all these different conditions. The conditions are these different angles. On the other side, so we have the string attached to the cart. It goes over a pulley, and then we have a suspended mass here. Now, what I did was I adjusted the mass on the suspended mass, so how much mass I put on there, such that when I gave this a little tap to overcome the static frictional force, the cart moved with like a constant velocity up the ramp. Okay, so it's not accelerating. We're purposely adjusting the mass so that when we give this a tap, it moves at a constant velocity up the ramp. And we do that for each of the different angles, right? So we have to keep adjusting this mass, tap this cart, and it's going to move at a constant velocity up the ramp. And the idea is to calculate the tension two different ways. To calculate it experimentally means analyzing the suspended mass. Now, if you look at the suspended mass here, right, there's two forces acting. You have a tension acting up, right, the tension in the string acting up. You have the weight of the suspended mass acting down. However, if this cart is moving at a constant velocity, so there's no acceleration, that means the suspended mass is also moving down at a constant velocity with zero acceleration. Since there's no acceleration, that means the sum of the forces in the y direction has to equal 0. Therefore, the tension is going to be equal to the weight. So if I know what mass is on here in kilograms, I can just multiply by g by 9.8, and that gives me the weight, but that's the same as the tension. So that's how we find the experimental tension. In fact, that's in the table here. To get the experimental tension, these are all the masses I had to put on there so that it moved at a constant velocity. So you're simply going to multiply these by 9.8, and that will be the experimental tension. Now, the theoretical tension is more complicated, right? So in theory, we should be able to calculate what this tension is pulling on the cart based on the information that we have from the cart. Okay, so actually, let me do that right now. So I'll try and derive this formula, and I'll do it on the iPad. Okay, so here's the situation, right? I have the ramp. It's at some angle. Right? Remember, we're going to vary that angle theta. You should really watch the video to see how I collected this data. And then there was a pulley. So a pulley over here. And then that wooden cart with the one weight was on the ramp. And we had a string connected to the cart. And then on this side, we had a suspended mass. And the idea was to adjust the mass, right? Adjust this suspended mass. This is like, think of this as M2. Adjust M2, this was M1, such that the cart moved up the ramp at a constant velocity. The idea was to move it up at a constant velocity. Constant velocity. Okay, and what I want to do is I want to figure out the tension, right? The tension in this string. So theoretically, what should that tension be? So let's look at all the forces acting on that cart. Let me draw this more carefully. So this is the ramp. This would be the angle theta. And this is my cart, right? So there's several forces acting on it. I have the weight, which is acting down. So that's the gravitational force. I'll call this W1, right? So it's M1G. I have a normal force, which is perpendicular to the surface, so perpendicular to that wooden ramp that's acting up. And then we had the tension that was pulling parallel to the ramp, right? That was a string. And then also, since it's moving, right, at a constant velocity, or it doesn't even matter if it's moving at all, it has a kinetic frictional force. So we have a kinetic frictional force in this direction, Fk. And remember, Fk is equal to mu k, that coefficient, which we know from earlier, right? Because we found that coefficient when we did the graph. Actually, we found it twice, but we're going to use the one where it was the slope of the graph where we plotted the kinetic frictional force versus the normal force. We know that that kinetic frictional force is mu k times the normal force. Okay, so first thing, create a coordinate system. Well, in this case, since it's moving along the ramp, I'm going to call that the x direction. I'll just call down positive. It doesn't really matter in this case, even though it's moving up, but that's fine. And then perpendicular to it will be y. Okay. And then if you notice, all the forces act along the coordinate system except the weight, but I can fix that, right? Let me find the components of the weight. So I'm going to resolve this into the y component of the weight, which is like this, wy, and then the x component of the weight, which is like this, that'd be wx. And remember, this angle theta that the ramp makes with the horizontal, it turns out that's exactly the same as this angle theta. Okay, so first thing, let's figure out the x and y components of the weight, what those are. So let me extract out that right triangle here. Okay, so remember, this is theta. This was wy. This is wx. Right? It's really w1y, w1x. I'll just call it. Let me put a 1 in there just to remind it it's 1. Okay, so w1y, w1x. And then the hypotenuse here is going to be the magnitude of that force, which is the weight. So this is just m1g, right? That's the magnitude of the weight. Now notice that relative to the angle theta, w1y is adjacent, right? And m1g is hypotenuse. So what trig function relates adjacent and hypotenuse? That would be cosine, right? So katoa, so ka is adjacent over hypotenuse. So we know that cosine of theta is equal to the adjacent side, w1x, divided by the hypotenuse, m1g. So therefore, I can solve for W1x, and it's going to be m1g times cosine of theta. And then W1x is, oh, hold on a second. I made a mistake there. This should be W1y, right? The y is adjacent to it. So this is y, W1y. And then opposite the angle theta is W1x, right? So this is the y adjacent, this is the x opposite. So what relates opposite to hypotenuse? That's sine, right? So I know that sine of theta is equal to W1x divided by m1g. And if I solve for W1x, it's going to be m1g sine of theta. Okay, so we have those two components. All right. Now what we're going to do is apply Newton's second law to this situation. Let me bring up the picture again. So let me first apply it in the y direction. So I have the sum of the forces in the y direction equals m1 ay. So I want all the y components, right? I want the y component of the normal force. I want the y component of the tension. I want the y component of the weight. And I want the y component of the kinetic frictional force. And that's got to equal m1 ay. Well, what is the y component of the normal force? So if we look at the normal force, right, here's the vector. All of it is in the positive y direction, right? So the y component of normal force is simply going to be all of n, right, the entire magnitude. What's the y component of the tension? Well, if you look at the tension, it's acting along the negative x direction, so none of that vector is in the y. So this is just 0. If I look at the y component of the weight, well, all of it is acting, but in a negative direction, and we just calculated it earlier. It was this, right? W1y is m1g cosine theta. And it's acting in a negative direction, right? So it's negative m1g cosine theta. And then how about the kinetic frictional force? How much of that is in the y direction? None of it, right? It's all in the positive x. So this is plus 0. And we know that this cart is not accelerating. It's not leaving the ramp at all in the y direction. So the acceleration in the y direction is equal to 0. And then if you bring this term to the other side, I can solve this for n. So the normal force in this case happens to be m1g cosine theta. It's m1g cosine theta. Okay, now let me go to the x direction. So in the x direction, I have sum of the forces in the x equals m1 ax. So again, I want the x component of the normal force, the x component of the tension, the x component of the weight, and the x component of the frictional force. That's got to equal m1 ax. Well, what's the x component of the normal force? Well, since the entire normal force is in the positive y direction, none of that vector is in the x. This is 0. What's the x component of the tension? Well, I look at the tension vector. It's acting to the left. Remember, I called positive x to the right. So it's acting in a negative x direction, all of it. So this is going to be negative t, right? The entire tension. What about the x component of the weight? Well, remember that was acting in the positive x direction, and we calculated it here. It was m1g sine theta. So this is plus m1g sine theta. And then what about the frictional force? Well, it's also all in the positive x direction. But remember, it's equal to mu k times n, right? The frictional force is mu k times n. So this is going to be plus mu k. And in n we just found from above, it's m1g cosine theta. Right? It's m1g cosine theta equals. And now what is the acceleration in the x direction? Well, in this case, remember that this cart is moving at a constant velocity, right? We're adjusting the mass on the hanger, so the cart specifically moves at a constant velocity up the wooden ramp. Therefore, its acceleration is 0, right, in the x direction. So this is just equal to 0. Okay. Now what I can do is I can solve this for t, right? I want to figure out what the tension is. So basically, I'll add t to both sides. I'll bring it to the right-hand side. And I'm going to get m1 g. I'm going to write this. I'm going to rearrange terms a little bit. m1 g mu k cosine theta. Right? I'll write that second term plus m1 g sine theta. And now since m1 is common to both terms on the right-hand side, let's factor it out. So I get m1g, and I'm left with mu k cosine theta plus sine theta. And that is exactly the equation that we want. So we're calling this like the T theory. This is like the theoretical tension. Okay, so let's go back to the hand. All right, so we just derived this equation, right? So T theoretical is m1g times the quantity mu k cosine theta plus sine theta. So in the table here, what you're going to do is you're first going to compute the experimental tension. Remember that dealt with the hanging mass, right? And since it was moving at a constant velocity, the acceleration was 0. So the tension in the string experimentally was simply equal to the weight of the hanger. So how do I compute that? Well, that's going to be m2 times 9.8, right? And then this one times 9.8, and that m2 times 9.8. So you're going to get all these theoretical experimental tensions. That'll be this column right here. And then the last column, the theoretical tension, that comes from this equation, right? So you're going to plug in the values. You need to plug in your different angles. For mu k, you're going to use the value from question 11 that came from the slope of your kinetic frictional force versus normal force graph. So use it from, where is it? It's all the way up here, right? So use this value, mu k, from question 11. And then the M1 here is simply the mass of the cart with that one weight, but that stayed the same through all the conditions. So that's just going to be 0.3529 for every condition. And G, of course, is 9.8 again. Okay, then what I want you to do is compare, well, actually, you're going to do two plots. You're going to plot T experimental, so tension experimental, this will be on the Y, and angle on the X, okay? And then you want to do a polynomial fit. There'll be some type of curve. And now using the coordinate tool, just like we did in the projectile motion lab, where I had to use that coordinate tool, I'll actually jump on Capstone in a second and show you how to do this. You're going to find the peak of the fitted curve, okay? And then that peak will give us basically an ordered pair, and the first value will be like the optimal angle, experimental, and then the maximum tension, experimental. We're getting those two values. So actually, let me show you this. So you're going to plot angle on the X, tension, experimental on the Y. Okay, so let's go. The usual, right, you choose classic templates, and then this upper left-hand one. For the x-axis, remember that's going to be angle for both when we plot the theoretical tension and the experimental tension. So this will be angle. For the units, you can either write in degrees, or if you have a keyboard, if you hold the Alt key down and you press 248 in a numpad and lift up the Alt, you'll get a degree symbol, or you can just write in degrees. Either one is fine. And then let's say this is my experimental tension. And in units would be newtons in this case. Okay, so remember my angles were like 20, 30, 40, 50, 60, then 65, 70, 75, 80, 85. And then let's say, I'm just gonna make up some somewhat reasonable values here. Let's say my tension was 2.40, 2.85, 3.20, 3.45, 3.60, 3.63, 3.63, 3.60, 3.55, 3.47, something like that. Okay, so now we choose angle, right, on the X, and then experimental tension on the Y. Remember, for the title, it's always Y versus X, so you could say experimental tension versus angle. That would be fine. I want to get rid of these line connections. So you hover over data point, right click, uncheck show connecting lines, the usual. And now for this one, we're going to do a polynomial fit. So we'll choose fit and go to polynomial. Okay, and it does a fairly smooth fit right through all the data. So what we want to do is we want to find the maximum tension experimentally, which means after I fit the graph, I want to find the peak of my curve. You don't want to use one of your data points. You actually want to find the peak of your curve. And then we want to find the angle at which that maximum occurred at. And we're calling that the optimal angle, experimental. So how do we do that? Just like we did when we did the projectile motion lab and we plotted range versus angle. Remember, we use that coordinate tool. So you want to do that here as well. So coordinate tool, go to add coordinates. We have to set it up first. You have to click on it, right click, tool properties, go to coordinates, and then change that snap to pixel distance to a 1, right? Just so it doesn't jump around. And now you should be able to drag this. Ooh, there we go. Drag it to the peak of your graph. Maybe right there. I can move this down a little if I want. Maybe right there would be the peak, okay? And then it gives you a coordinate pair, right? And the first value obviously is going to be your angle. So that'll be your optimal angle. And then the second value, that's this value right here, that's going to be your experimental maximum tension, right? So those are the two values that you want. And then the usual, you want to include this graph. Make sure you include this graph in your lab report. So you hover over the border, right click, copy display, and paste it into your group lab report. Okay, so you're going to do two graphs. You're going to do one for experimental tension and one for theoretical tension. All right, let me go back to the handout. Okay, so again, for both graphs, right, theta will be X, and then tension will be Y. In the first graph, experimental tension will be Y. In the second graph, your theoretical tension will be in the Y. So you want to locate, using the coordinate tool, the maximum experimental tension and then the optimal angle, and then do the same thing for the theoretical versus angle graph. Locate the maximum tension theory and the optimal angle theory. Those values will go in this final table here. Okay, so this is experimental, both the tension and the optimal angle, and the same thing for the theoretical graph, tension and angle. And then you want to compare these two by computing the usual percent experimental error, right? Think of the theoretical as the accepted one. So when you compute the percent experimental error, you want to divide by the theoretical one. Make sure you show me all your calculations. So make sure you show me these two calculations here. And hopefully they're close, right? Because in theory, the experimental tension that we got by calculating the weight of that hanging mass, that should equal the tension that we derived from that longer theoretical formula, right? In theory, they should be the same. All right, so that's it for this particular lab. And next time for lab 5, we will actually be looking at different things. So Physics 212 will be looking at work and energy, and the other classes will be looking at torques. Okay, great.